when it's a different transformation, namely when the transformation is about multiplication of a constant, which is something like this right now. Okay, so this is the second kind of transformation that you should be expected to know how to construct. So again, if you have a PGF of x to be 1, 2, and 3, probability is 1/4, 1/3, 1/4, and 5/12. If I ask you to construct the PGF of y right now, based on the transformation stated, there are a few ways of you will see that the third method from before no longer works. Okay, you cannot just multiply by 2 throughout. So again, the PGF of x here is just 1/4 gxt is actually equals to 1/4 t to the power 1 plus 1/4 t2 plus 5/12 t3. Okay. So remember, by definition, under a PGF, the outcome is the power. Okay. So if you really want to do it, from the table perspective again, construct the table for y. So you will have 2, 4, 6. And the probability will be the same. Okay. It's just 1/3, 1/4, and 5/12. Then from there, you can actually construct the PGF of y immediately. So this is just 1/3 t squared plus 1/4 t to the power 4 plus 5/12 t to the power 6. And then this will be the answer for the PGF of y immediately already. Okay. If you want to go through the polynomial definition, it's just gyt Okay, and then remember, y is equal to 2, 4, and 6 is the same as x to be 1, 2, and 3. But the outcomes of y do not change. Okay, so it's still the same. Okay, then you fill in the blanks, and then you'll be the same answer as this. Okay, so as a rule of thumb, how does the PGF of y stack up against the PGF of x, right? It's actually the same coefficients, but the powers have doubled. Correct? Because remember, PGF power indicates outcome. So under this stated transformation here, 2x means the outcomes are all double. 1, 2, 3 became 2, 4, 6. That's all. Okay, not that difficult if you think in simple terms. Okay, but the probability stays the same, so the coefficients stay the same. That's all. With the transformation above, plus 3, all the coefficients got bumped up by plus 3. Okay, I erase the PGF of x. If we can construct the PGF of x, the powers will be 1, 2, and 3, right? Plus 3 to all of them, it became 4, 5, and 6, respectively. Okay, but of course, you need to kind of show some working in the paper 3. You cannot just write down the answer right away. Hence, these are the 3 various ways which you can go through to construct the updated PGF. Okay, so one transformation is on addition, one transformation is on multiplication. All right, so the third kind which you can expect will be the combination of both transformations. So same gameplay again. When the time comes, just don't get confused by this to do. So if you have x to be 1, 2, and 3, now just write a, b, and c. Okay. So the PGF of x is just a t to the power 1 plus b t squared plus c t cubed. Okay. So if you want to construct 2x plus 3, immediately if you want to, you can just write down y. So this will give you 5, 7, 8 times 3, 9. Okay. So the PGF of y is just equals to a t to the power 5 plus b t to the power 7 plus c t to the power 9. Okay. You must always be able to be quick to figure out how will the outcomes be updated based on the transformation stated. Okay, that's all really. Okay, can you understand this? Everyone?
Yeah.
Okay, so this should not be difficult, okay? And you should not get stressed by this. As long as you stick to the definition, you won't go wrong on this, okay? So in terms of the abstractness of the PGF, right, this is it already. Nothing special beyond this, okay? Now the problem is your four standard distribution, discrete distribution. Remember we went through that PGF is only applicable for discrete random variables, right? After doing so much work on the standard table, probability distribution variable, and their PGF, right, you are bound to encounter the four standard stuff, your binomial, Poisson, geometric, and negative binomial, okay? Now, this chapter, right, is tied strongly with geometric and your geometric series because it has a lot of gameplay pertaining to these two chapters. Okay, for binomial and Poisson, not so much. But if you really want to construct the standard issue for a binomial, right, I actually don't have my summary notes with me here, but they are not inside the standard formula sheet, and you don't have to memorize them at all. Okay, so let's say for a binomial, if you have n and p, okay, then let's just construct a table for binomial. If you have x, 1, 2, 3, 0. If you have 0, 1, 2, all the way until n, okay? Their individual probability, this is actually q to the power of n. This is n choose 1, p q to the power n minus 1. This is n choose 2, p square q to the power n minus 2, okay? This is p to the power of n, okay? If you wish to construct the probability table for a binomial, okay? So I hope you all still remember your PDF, all these things for binomial. So how would the PGF for a binomial distribution look like, right? It will kind of get ugly if you work from definition, right? It will be like qn t to the power 0 plus n choose 1 p q to the power n minus 1 t to the power 1 plus n choose 2 p square q to the power n minus 2 t2 plus dot 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 until p to the power n t to the power n. Okay, this is constructing the PGF or a binomial by definition. Okay, just give me a minute to construct the. Okay, so the formula for this, right, is pretty ridiculous. So let me just see how to put it in a nicer form for you. Okay, so you can see that this is the by definition of the construction, right? Okay, by looking at the table above here. All agree so far? Yes, no, yes. Everybody can follow?
Yeah.
Okay, then I can actually rewrite this into another term. So I will group, see how I group. So you have qn t to the power of 0 plus n choose 1 pt to the power of 1 q to the power n minus 1 plus n choose 2 pt square q to the power n minus 2 plus dot 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 plus n choose n pn ptn. Okay, so actually this is a binomial expansion, right? And this can be broken down into pt plus q to the power of n. Okay, from the bottom to the top is actually binomial. From here to here is binomial expansion. From here to here is actually binomial factorization. But I don't want to confuse you with more work right now. Can follow? So actually this t to the power of 0, you can think of it as p to the power of 0 also. Okay, so across all the terms, then n choose 1, n choose 2, n choose 3 are just standard coefficients of a binomial expansion. Understand? Can follow? Yeah. So you can see what does this tells us, right? a binomial distribution somehow is PGF. When we want to represent it as a function, it became a binomial expansion. Okay, that's fine enough for us. But don't you see that if I give you something like this, if I tell you, hey, I'm thinking of a variable, I do not know what distribution it is or whatsoever, but I do know its PGF looks like this. Then all the results that we have been discussing in the first hour comes into play right now. If I want you to if I give you the PGF like this, then t, remember t is a dummy variable, which means I will give you something like this, 1/4 t plus 3/4 to the power of 10. So I say, hey, this is the PGF of the variable that I'm thinking of. And there is no way you can construct the table. To construct the table, you need to extend this to the power of 10 out. And then you have a total of 11 terms, right? T ranging from power 0 to power 10. Then you will do until you are nuts. However, if I give you this, you can actually just differentiate and let t be 1. You get expectation immediately, right? Or if I want the probability x to be 3, just differentiate this thing 3 times and then let t be 0 divided by 3 factorial. And then it's a lot more convenient in that sense. Understand? And you can differentiate this easily using chain rule, right? Or use a GC to differentiate this for you. Understand? Can you understand this?
Yeah.
Did you just say that like for this one, then you just let, so I put like, let's say t is 1, right? Then like 1/4.
You can let t be 1. You must differentiate first, then you let t be the thing. You must go through the differentiation first. Right?
Oh.
If I ask normal function, if I say calculate f double prime 2, you let x be 2 first, or you differentiate 2 times first.
Oh.
Understand?
Okay.
Yeah, you can. If you let t be 1, it becomes a constant already. I wanted to differentiate, correct?
Okay.
Okay. So you must differentiate the function first, then you let the variable take out the value in point. Okay. So all these special distributions, all the table distributions that I had above were brainstormed by me with no pattern, right? But when a particular variable follows one of the few standard distributions, right, the PGF tend to be able to be compressed into a closed form like this. When it's closed form like this, a computer can process this extremely quickly and easily, but without going through like a polynomial style. So even if today my binomial distribution has got 100 outcomes, it can be compressed into a standard binomial form, factor form like this, right? I can differentiate this and then let t be 1 or whatsoever very easily, and then I can calculate its expectation and all these things without really knowing its parameters explicitly in that sense. Okay. So this is the main point of strength of PGF. It doesn't really make much sense from a academic exam taking perspective due to your time constraint on the 1 hour on paper 3, but it will make sense from a computational perspective. That's all. Okay. So this is for binomial. Okay. Do you need to memorize this thing? You don't have to. Okay. In the actual test or exam, if the school wants to test you, right, they will have to tell you as part of the question, oh, it is known or well established that the binomial distribution has got PGF like this, and so on and so forth. Okay. So you don't have to memorize this, but the results prior, you need to memorize all this transformation stuff. Okay. And so this tells me a binomial variable will have such a following PGF. If a variable's PGF is not like this form, right, it is not a binomial distribution also, which is one of the results that I skipped over quickly just now. Understand? So if a PGF, no matter how I compress it, right, its form is not like this, the yellow highlighted one, then it's not a binomial distribution. Okay? So if I have something like this, 1/3 t plus 1/3 to the power of 6, then this variable here is not a binomial distribution, because binomial distribution, you must have p and q, right? And p and q must sum to 1. So based on what I have here, these two numbers don't sum to 1. So this is not a PGF of a binomial distribution. Hence, this variable is not a binomial guy, even though it's still a distribution somewhere out there. Okay, understand? Okay, so this is all the effects of PGF coming in. Okay, so a lot of simple stuff you may think, oh, like, so obvious, why study this? Then actually, I mean, for exam's sake, they will trick it in a way that's meant to test you on stuff. That's all. Okay. So the next one must be Poisson. So Poisson even worse. So if you have, so obviously you know that the PGF of Poisson is bound to have some exponential stuff popping in. So Poisson like this. Okay. So the table will be 0, 1, 2. The worst part is Poisson is endless. unbounded at the top. Okay. So if you want to calculate its probability, so this will be e to the power of negative lambda. This is e to the power of negative lambda, lambda to the power of 1. E to the power of negative lambda, lambda to the power of 2 over 2 factorial. Okay, and then so on and so forth. So these are all computed based on the PDF of a Poisson distribution. So if these are all in place, you can actually construct the PGF of a Poisson variable. It will look like this. It will be e to the power of negative lambda t power 0 plus e to the power of negative lambda lambda t to the power of 1 plus e to the power of negative lambda t to the power of 2. Sorry. E to the power of negative lambda lambda square t to the power of 2 over 2 factorial. Then plus dot dot dot. Okay? So this term, and this term. You will see that these three terms do not follow an AP or GP at all. Even though I can factorize out e to the power of negative lambda, all the t's seems to follow a GP. However, there is a lurking coefficient of this thing, and 2 factorial. And then the next one will be 3 factorial, and so on and so forth, which cannot be accounted for by a standard GP. Okay? Understand so far? So this thing here is not an AP or GP at this point in time. But somehow by the advanced calculus technique, right, which is actually covered in the paper 3 calculus side, you will know how to factorize this, and the factorization is actually, let me just double check. Oh no. Okay, so the PGF of a Poisson variable happens to be like this. Can be this thing here can somehow to be compressed to be this e to the power of negative lambda t minus 1 now. Okay. So again, it became a compressed form. So intuitively, we know that a Poisson should have an e because its PDF contains e. But somehow this power here is totally non-intuitive. Okay, but the mathematics dictate so. Some of our teachers will go through, some of our teachers won't go through. So depend on your style. Okay. So again, you need to memorize this. Don't have to. It will be inside the question when the time comes. So they will tell you how will the question be phrased, right? They will tell you, okay, it is now known that a Poisson distribution should have the following PGF, where lambda is the mean. Okay, show that whatever distribution, show that now I have this distribution, show that it actually follows a Poisson distribution. So you are supposed to show that the PGF of the variable in question, right, can be simplified into a form like this. Okay, then so the fundamental thing is this multiplied by t minus 1, and then whatever coefficient this is, it is the mean of the Poisson distribution. From the closed form version, you are supposed to be able to extract the relevant information, in particular the parameters of the distribution. Just like just now, this binomial distribution, we must know that the coefficient attached to t is the probability of success, and the power is the number of trials. This here is simply the complementary number to probability, which is the failure rate. That's all. Okay. Whereas for a Poisson distribution, it's an exponential function. Its PGF is an exponential function in compressed form. Okay. Then the coefficient of t minus 1 is actually negative of the mean. So again, once you have this, are you able to construct the mean, variance, and everything else easily? You can, right? You can differentiate this easily using chain rule or whatsoever, without really knowing much of the situation. Okay.
Wait, so this is the simplified version of the PGF of the Poisson distribution?
Yeah, this can somehow be factorized into this. Okay, the details you don't have to go through.
Okay.
Okay, just know that this is the generic form of a Poisson PGF, and is e to the power of t minus 1, then with negative lambda, that's all. Okay?
So you're saying that like if the in this case for the Poisson, right? Like is it like if it each term, so we only have one term in the distribution, then I will get this thing in red, this expression in red that you suggested, right? But if I have like two,
say that again. Oh, so
if like, are you saying that regardless of how many terms, let's say there are like 3 or 4 terms for the GXT, right?
For Poisson,
then
or for Poisson,
yeah,
or what? No,
Poisson.
Poisson, this is an infinite summation, right? Because Poisson has got no upper bound in the table, right? The possible values for x has got no limit. I can keep on writing this summation for x to be 3, 4, 5 until infinity. Hence it's plus until dot.
Okay.
But this summation, this infinite summation, right, through advanced calculus technique is known to simplify into this.
So in the exam, is it that as long as you get like this expression in red and the final thing that you do the arrow, the one in red, as long as you get this expression, then it's like proven it's a Poisson or something like that.
You must show that the desired formation is this. That means you need to show that something follows a Poisson, right? Its PGF must be e to the power of negative, then something times t minus 1.
Oh, so like prove it, is it? Oh.
Yeah. You're supposed to show that this particular variable's PGF is supposed to adopt such a form, and if we have such a form, then it must be a Poisson with mean this guy.
Oh, okay.
So for binomial, right, it must be of the following form, like triangle t plus square. To the power of like circle, then triangle plus square must be equal to 1. Then this circle here must be a positive real number, which is an integer, which is a number of trials. Okay? If a variable has got PGF of such a form, then it is a binomial distribution with the following parameters. Okay? If it doesn't, then it's not a binomial distribution. Whatever distribution it is, but just not binomial, that's all. Understand? Yeah. Okay. So these two set up the ground rules for like what is the standard distribution, standard PGF of all the distribution that you have, at least the two that you have studied, that's all. They lay the like everybody must follow this framework. If they don't follow this framework, they're not my distribution, basically. Okay, so these two, the formula is like bothersome to memorize. Like you don't have to memorize, okay? But you do not need to know how to derive them. But for geometric, you have to, because geometric will obviously become a geometric Sn or S infinity, that's all. So geometric is P, right? So X is the number of trials you need to hit your first success. So you have X to be 1, 2, 3, ... infinitely, because you can keep on failing. So this will be P, QP, QP, Q square P, and so on and so forth. Okay, and then it's good enough for us already. So usually 3 terms is good enough. Okay, 2 terms is not sufficient to see a pattern. 3 terms is the bare minimum. So the PGF of such a geometric distribution will be GXT is equals to, okay, I'll start from definition. Okay. Okay, X starts from 1 in this case simply because geometric, the minimum value is 1. Okay, so here we start to fill in the blanks. This is just P t to the power of 1 plus Q P t square plus Q square P t cube plus ... Okay, if you look at this, this should remind you that this is a GPS infinity. So feel free to write these things down in the actual presentation. So this is a GP S infinity. Okay, U1 is PT, common ratio is equal to QT. Okay, or simply 1 minus PT, up to you. Okay, can follow so far? So like this, like this, like this. Okay. Then if I were to compress this using the GPS infinity formula, I will have pt over 1 minus qt, or pt over 1 minus pt. Okay, so they will always, so this is the one where they will ask you to prove from scratch, because geometric, right? Okay, the binomial and Poisson, you will see that I actually, okay, binomial is a bit hardcore. You need to, a minute. Okay, binomial is hardcore in the sense that you need to recognize the binomial expansion, right? Which is set as an exam question occasionally based on the IB past year papers, okay? Because you need to see the trick involved, okay? But this one, you will give a bit of guidance question. Poisson, you don't have to do it because this factorization technique, right, is way beyond the syllabus, okay? So let me just tidy things up a little bit here. Oh, shucks. Okay, let me, I'll tidy this up later. Okay, for geometric, right, you will see that the techniques that I use only use basic mathematics that you have been learning for the last 2 years, okay? In particular, GPS infinity. I constructed the table from scratch like this, and I didn't change anything else beyond that, right? I constructed the expression from scratch. Oh. I constructed the PGF from scratch. It's getting worse. I constructed the PGF from scratch, from definition. Then I push in the relevant stuff based on the PDF of a geometric distribution, right? Then from there, it was a GPS infinity. Then it got compressed to be a nice expression here. Okay, this is the one where you may be asked to prove in the actual situation. So what they will do is they will say, hey, I know X is geometric distribution variable, probability of success is 1/4. Can you show me, can you prove that its PGF is whatever it is? So you must start from the definition like this and then go through the process, okay? You don't have to write on the table, of course. If you are confident to write down the polynomial right away like this, go for it, okay? Can? Understand? Okay, so you can see all these classic distributions will come back in these various forms, okay? Okay. Now the last one will be negative binomial. So for negative binomial, if you were to go through the stuff, right, you will go nuts, okay? So for negative binomial, right, let's just go through the process first. X is negative binomial, let's say 3 1/4. Let's just say if probability X is equal to 7, it means probability 7th trial is 3rd success. Okay, this is just the situation. Okay, for negative binomial, just reminding you guys first. Then you will realize that it's practically impossible to draw out a table for this. If you want to have X, then minimally you need to have 3. Minimally you need to have 3, 4, 5, 6, 7, and so on and so forth, right? And each individual number is extremely hard to write down the probability already. Okay, for a negative binomial. It's so complicated that it don't even exist in your GC, the negative binomial function. Understand so far? So it's extremely difficult to construct the PGF for a negative binomial of a table, of its own, in fact. So to handle negative binomial using the angle of PGF, right, is to recognize this. A negative binomial, right, is actually a sum of geometric. So for example, if I want a negative binomial 3 success like this, right, it's actually X is actually Y1 plus Y2 plus Y3, where each Y is actually geometric 1/4, same odds of success, of course. Can you understand so far? But it's 3 separate geometric variable, but from the same distribution, that's all. Okay? So what do I mean by that? because based on what I wrote here, right, I want to have 3 successes, right? Geometric just nice measures the number of trials you measure until you hit your 1 success. So you can see your X like this. It's like, oh, you play and play and you throw and throw and throw until you have your first success. Once you have this, you press the timer and start counting again. Then you throw and throw and throw and throw until you have your second success. Then until you have your third success. So functionally, this is your Y1, Y2, Y3. So collectively, it gives you 3 successes. Each of them is like 1 geometric and 1 geometric. Can you understand this picture here?
Yeah.
Can you understand?
Yeah.
Yes, no, yes.
Sort of.
Okay,
Yeah.
so can I understand the narrative here? You must make sure you are okay with this first, okay? Everybody can follow?
Yeah.
Can.
Then with this, right, you can mix up the results from here, which we have already established very easily, and the ones above. The PGF of an addition of variable is simply the multiplication of their individual PGF. Each of these individually geometric, and geometric. So we actually know how they would fall under, right? So now if we have X is negative binomial R and P, right? If you have Y is known to be geometric P, PGF of Y is simply P, let me check it out again, PT over 1 minus QT. Okay, so we know that X is actually Y1 plus Y2 plus dot dot until YR, okay, because you want to have R successes. So from here, you will see that this is actually just PGF of Y1, PGF of Y2, dot dot until the PGF of YR. Okay, the multiplication of the individual PGF, and then this is just, they all come from the same distribution, right? Which is this guy here. So they should all have the same PGF. So it's just PT over 1 minus QT to the power of R. Okay, a negative binomial. Yeah.
So can you explain why it's multiply the PGFs? Why don't you add them together?
As in addition of variable is multiplication of PGF, is it?
Oh.
This,
Okay.
this one I'm just using the result that we had at the start of lesson, remember?
Okay.
Yeah. Okay, so to be more mathematical, the PGF of X is actually the PGF of like Y1 plus Y2 okay, like this. Can you understand, everybody? So this is how the PGF for a negative binomial is obtained. Okay, even though when we talk negative binomial, we didn't really emphasize it's like an accumulation of geometry, right? Because we want you to understand how to construct the negative binomial from scratch. But over here, different gameplay. So we have to make use of this logic over here. Can you understand? Yes, no, yes. Everybody, any questions? Any questions offhand first? Okay, again, I don't expect you to master this off the charts like this immediately, of course. Okay, but as of today, as long as you're aware how to construct a PGF, the narrative behind it, polynomial first, then from polynomial you can get the outcome and then expectation, all these things we'll do, and then you can see the flow of things. The hardest kind of question will always be the substitution question. Okay. Okay, everybody. Any questions for this as of now? Based on the content first. Anyone? No. Okay. Or you don't see how it comes into play, right? Okay. Go take a few minutes break first. Then after that, I'll go through 2 past year paper questions with you guys. Okay, Ken?
Okay.